So today we're going to look at graphing and solving quadratic inequalities. So we've talked about the equalities and we've talked about inequalities in the past. So now we're just combining those two things. Before we were looking at linear. So it looks something like this, for example, and then we would shade underneath, or maybe we would say it was dotted or dashed, and maybe we shade above, right? And we had systems of linear inequalities, which we would say, okay, if it works for orange and it works for yellow, then this is the solution for the system. Same exact concept, except for now we're doing it with quadratic functions. So there's basically two different types of curves that I can draw. One is going to be a solid or a bold curve, and that will include those points. And then I'm going to have a dashed or dotted curve where it does not include those exact points. So the ones that will include the points and have a bold will be these ones over here, where it's y is less than or equal to, or y is greater than or equal to. The ones with the dashed are going to be y is strictly less than, or y is strictly greater than whatever my quadratic function is. So I'm going to just do two super quick examples here. First one, I'm going to say y is greater than or equal to x squared. It's going to more or less look like this, and I'm going to shade everything on top of the curve. So since y is greater than or equal to x squared, I shade above. If it was y is less than or equal to, then I would shade below. And we can pick a point and test it out, and we're going to do that in a minute. If I had something that looked like y is less than, strictly less than, x squared, I would have a dashed curve here, and we would shade below. So just super quick how those two things would look, and then again we're going to combine different versions of these where maybe we've got a couple overlaid on top of each other. So when we're graphing a quadratic inequality with two variables, there's a couple things we want to keep in mind. The first is that we're just going to draw our parabola, and then we're going to make sure whether it's solid or dashed based on the inequality sign. From there, our suggestion in these instructions is to pick a point inside the parabola and clearly check whether it works. I'm going to tell you that we can always use this above or below description that I used here. So if the y is greater than, it's going to be above the curve. Keep in mind, my curve could open down, and above now means this stuff here. So just keep that in mind. But if you want to pick a point and test it out, we can always do that as well. If the point works, we're going to shade that region. If the point doesn't work, we're not going to shade that region. So here we have an example that we're going to take a peek at. So this is saying y is greater than this thing. As I look at this example, if y is strictly greater than stuff, it means I'm going to have, first and foremost, a dashed line. And then the second thing I want to note is that this thing is going to be shaded above. So I'm going to shade above. Whoops. There we go. So looking at this, I'm going to say, okay, can I graph this thing? Yes, of course, right? We've graphed a bunch of these. So if I were just pretending it was y equals x squared minus 2x minus 3, we can definitely graph this thing. So I'd suggest maybe doing, if you want to graph it from standard form, we would do our negative b over 2a, and we would see we get an x value of 1. So that x value is for my vertex, and then I'm saying, okay, well, take that and plug it in to find the y. When we do plug it in, we get a value of negative 1, 2, 3, 4 here. So vertex for this thing, just for the record, is 1, negative 4. And now as I look at this, I'm saying, okay, well, what does that mean for me? Like, what am I going to do with this information? Well, what I'm going to do is I'm going to graph this thing. So we set up our t-chart, we set up our graph. Keep in mind that we said it was going to be dashed. So here we're going to get dashed lines, which we see. Not very good dashed lines. They had better dashed lines before, but you get the point. And then I'm going to use this example where they're picking a point rather than just using this information that we shade above. We do definitely shade above here, but let's test the point out. So let's say we wanted to check this point 1, 0. Now, if I'm graphing something, the easiest point to check is either going to be 1 directly above or 1 directly below my vertex. I personally love to use 0, 0 if it is clearly in or out. If it's even the slightest bit in a vague region where I'm like not totally sure, then I will not include it. Now looking at this one here, I see I have a 0 at negative 1, 0. So this x-intercept here means that I'm crossing, and I know that 0, 0 is going to be either in or out of this curve here. And by that I mean inside up or outside down. So if I want to use 0, 0 here, I could, but I'm going to choose 1, negative 3. So I'm choosing 1, negative 3 again, because I want to pick a point that is super close to my vertex, just either directly above or directly below it. So it's super clear whether it's in or out. So this thing's going to get plugged into my equation. So let's say negative 3 greater than 1 squared minus 2 times 1 minus 3. So 1 squared is 1, minus 2 minus 3. So simplifying here, so now I got 1 minus 2 gives me negative 1, minus 3 gives me negative 4. Last time I checked, negative 3 was greater than negative 4. Yep, so since this works, this green point here is included in the region we want, and that's how we'll know to shade all of this. Now let's say, for example, I picked a different point. Let's do this one down here, right? If I did this point in purple, this point 1, negative 5, and I plugged in this value, I would get negative 3 greater than 1 squared minus 2. 2 times 1 is just 2. I get minus 3 here. Whoops. It's supposed to be a negative 5, not a negative 3. There we go. And so now looking at this, I know that this thing on the right is going to simplify to negative 4. The thing on the left is negative 5. Is negative 5 greater than negative 4? Nope, it is not. So since it is not, we do not shade that area. So this thing sitting over here doesn't work. We do not shade it. So that's how we test it, by plugging in a point. Here we have an example. So I've got a board. The board has just some length and width, but the thing that I care about is the thickness. So this sort of height here. So this height D is used in this formula where the weight that it's able to bear, W, is less than or equal to 300 D squared. I have no idea if this is an actual legitimate equation or if they just made it up, so keep that in mind next time you go try and put 300 pounds on a 1 inch thick board. When we look at this thing, we want to graph it to start, and then from there we want to test to see if this 0.75 inch thick board can support 60 pounds. So when we do this, it's going to be a less than thing. So the W is sort of representing our Y now, and then this D is really our X. So in terms of like how we're used to graphing it, just keep in mind that the variables don't really change anything. We just have our W labeled for our Y-axis and D labeled for our X-axis. So we should be able to graph this thing pretty quickly and easily. Vertex at 0, 0, it's just going to go up from there. Now the reason they're not including the negative portion of this graph, I'll just kind of like fill in what it would look like, is just tell me when the last time you saw a negative thick board. Yeah, me either. I don't know, right? It doesn't exist. So we do have a practical limitation here, which is the thickness of my board must be greater than 0, right? So if it is 0, that thing disappears. Negative, I don't know. My little tiny human brain can't even comprehend it. So now as I look at this, I'm saying, okay, just doing the right half of this thing, it's Y is less than stuff, so I'm going to shade below. It's less than or equal to, so this is going to be a bold line, and I just shade all that stuff below. Then I take my point and test it out. So I want to see, okay, what is this 0.75? 0.75 puts me right here, and then 60 puts me right here. That's how I get this point. So plug that in, test it out. Does it work? Yep, we're good to go. So I'll just hover over that for a second in case anybody wants to see their explanation or work done out for the second part. When we want to graph these things like a system, so just like I talked about in the very beginning here, super similar to what we've done in the past, we're basically just going to have two versions of this thing. I'm going to do the one right here in red, the one right here in blue. We're going to graph both of these things. So again, if you're having trouble graphing, make sure you go back and check out that initial graphing stuff that we did. The only thing different is how I draw the curve, whether it's dotted or bolded, and whether I shade above or below. With this one, I'm going to say this is bold because it's y is greater than or equal to, and I'm going to shade above since it's greater than or equal to. So I'm going to shade above this thing. So that's where we see this bold line here for the red, and that's where we see all this stuff shaded up in here. I'm going to get rid of my shading just because their shading is more clear. For the next one, again, we're going to graph this thing, except for this time it's going to be dotted. So dotted or dashed, however you want to think about it. And then for this thing we have y is less than blah blah blah, so this thing is going to shade below. So that's why we see dashed lines here, dash, 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 and we see the shading below on this one. Now for my common bounded region, it's going to be this stuff right inside here. So I got to be above the red and below the blue, so it's this stuff right in there. When you guys are doing graphs, just make sure that it's clearly denoted one way or the other. One easy way of doing this is just using like a little curve for the shading. So I'll show you what I mean by that. So if this were my graph, again, I'm just doing a super quick version of it. But I'd say this, and then I'd say something like that. And then for my actual shading on this thing, I'm just going to do a little wiggly line where I do want to shade. And I do a little wiggly line where I do want to shade, but then the only thing that I actually end up shading is where both of those things overlap. So that way when I'm looking at this, it's very straightforward that the purple is the only actual shaded region. If you did your shading where you shaded all this stuff in, and you did your shading where you shade all this stuff in, it can be pretty hard for me to tell where that common bounded region is. So just keep that in mind. Don't go crazy with the shading. Here we have a quadratic inequality with one variable. So when I'm looking at these things, I'm basically saying, okay, where is this thing going to be, less than some value or greater than some value, and we can also do less than or equal to, greater than or equal to stuff. To do this, we can use a graph to solve, and so when we do it, we set it up, and then we solve using that information. So we'll look at the first one here. It's better if I just step through an example rather than try and explain it. I mean, I can read through this, but it really is, I think, more confusing for more folks than just going through the example itself. So let's see x-axis, x-intercepts, and then solve. So looking at this thing here, I basically want to graph it, and then I want to look at the graph and see, okay, what's going on? So I've got my vertex right here. I have an x-intercept and another x-intercept. So these are two coordinate points, one at 1, 0, and this one at 5, 0. This right here is at 3, negative, 4. So if I wanted my vertex here, just for information purposes, it's at 3, negative 4, but we don't really need that. The thing that I'm really concerned with is where this thing is going to be less than 0. So what I can do is I can plug in a value to test out if it works or not. So I could pick a value in between here and plug it in, or I can just think about what's actually going on here, right? If I were to sketch this graph and I were to say, okay, well, instead of it being like, this stuff is less than or equal to 0, if I said y is greater than or equal, greater than, strictly greater than this stuff, where would I shade on this graph? This graph would be shaded like this. So therefore, these points that work are going to be on the inside here. If it was strictly a greater than, and then y was the less than thing, it would be shaded on the bottom, and it would be the outside region. So when I look at this, let's plug in a point. let's pick a point, I don't know. We'll pick this point here, 3, 0, right? So let's plug in 3, 0 into this thing. There's no y's we're plugging in, so let's just pick a value. So let's just plug in 3. 3 squared minus 6 times 3 plus 5 less than 0. Is it true or is it false? So let's look. So here I get 9 minus 18 plus 5 less than 0. Last time I checked, this is going to be negative 9 plus 5 is going to be negative 4. Is negative 4 less than 0? Yes, it is. Check. This thing is good to go. So I'm going to have all these values right along here. So between 1 and 5. And again, if I wanted to solve this thing by factoring, I'd factor it to look like this. 99% of the time, I'm going to solve by factoring. If you do want to sketch a graph first and then the graph lines up nicely, that's okay too. Just keep in mind that if it doesn't, we're definitely going to want to solve algebraically first. So as we look at this thing, the way we write our answer is we would say x is less than 5, but it's greater than 1. So the reason it's strictly less than and strictly greater than there is because this is not a less than or equal to. Here we have a super similar example, so I'm not going to spend a ton of time here. The only thing different is that now we're saying, okay, this is greater than or equal to 0. So imagine I popped a y into this thing, right? So I'm saying, okay, where's this stuff going to be greater than or equal to 0 for my y? Well, y is less than this stuff. Where do I shade for my less than stuff? I shade on the outside. Or excuse me, I shade below. So this is going to be what's shaded, and I see that this is what I'm going to get for my region. So now let's look at this thing in terms of solving algebraically. It looks like nasty numbers to me, so that jumps out as a quadratic formula opportunity. So I'm going to plug that in, and I get this right here. Don't use the approximately 0.69 and the approximately negative 2.19. Leave it as this. For graphing purposes, if you want to do that, just to like give yourself an idea of where those values are, totally fine. Just make sure if you're actually putting an answer that we're using this as our answer. So when I look at this thing and I'm wanting a final answer here, I'm saying, okay, well, let's test a point. 0, 0 is a pretty tempting point to test out, as I love just plugging in 0. So again, I can either plug in something on the inside or something on the outside. It's always going to be one or the other. It's not going to be like it opens to the right from this point and it opens to the right from this point. It's either they're both out or they're both in. So let's plug in 0, 0. Super easy to plug in 0, 0, negative 3, greater than or equal to 0. Nope, not the last time I checked. So when I look at this thing, this point here does not belong on my solution line, so I do not include this. It would be strictly on the outside. Since it was greater than or equal to here, it's going to be greater than and less than respectively. So the answer I'd be looking for is x is less than or equal to negative 3 minus root 33 over 4, and that I get x is, so I'll put a little comma here, and we also get x is greater than or equal to negative 3 plus root 33 over 4. So that's what I'd be looking for an answer on this one. For solving a quadratic inequality algebraically, we're going to do the same exact steps as we did before, except for we're going to find our zeros and then test a point from there. And we kind of refer to this as a critical x value. So we know that things happen at these critical x values, but we maybe don't know what exactly happens. So we're going to use a number line for this method here. So if I started with this, I want to get it to a form where I've got it set equal to 0. I'm going to pretend that my inequality sign is an equality sign. So that's the first thing I'm going to change. So I'm going to change this into x squared plus 2x minus 8 equals 0. And I want to solve for this thing. To solve, it could be that it factors nicely, and if so, I want to do that because that's pretty quick and easy, but maybe it doesn't, and if it doesn't, that's okay. We'll use quadratic formula just like we did in the last one. Ugly numbers, but ugly numbers are still numbers too. So now I've got x plus 4, x minus 2 into what this thing factors into. So I get my actual x answers. So my x's are -4 and x equals +2. The reason being is I set these each individually equal to 0, right? So I set that equal to 0, and then I set that equal to 0, and I solve for my x's. So these are my two critical points here. So I draw my number line. I have a critical point at 2. I have a critical point at -4. This thing was a less than or equal to, so instead of being open circles, these are going to be filled in circles. So I got filled in circle there, filled in circle there, and I'm just trying to figure out, is it between or on the outside? So I'm going to pick a point. 99% of the time, if 0 is an option, I'm going to pick 0. So I'm going to try and see, does 0 work, yes or no? So I'm going to plug 0 back into the equation and see what it works. See if it works, excuse me. 0 squared is 0, plus 2 times 0 is 0. Is 0 less than or equal to 8? Yeah, last time I checked it was. So check. This works. This is now my shaded region. I am done. So we have now solved this thing algebraically using our critical values on a number line here. The way that I would represent this answer is I would say x is greater than or equal to -4 and less than or equal to 2. That would be my final answer here. We see that we can also test points on the outside, so if we wanted to, we could say, okay, let's test out 3, oh, let's test out -5, and we'll see that both of them do not work. Using quadratic inequalities as a model, so when we're looking at these things, we can model with them. So basically this is just an equation for breaking time. So the reaction time here to a visual stimuli, I guess it doesn't specifically say breaking, but reaction time. And this is the model. So we have, whoops, that's a little too much there. This is the model. So here's the model, and here are the ages. So we're saying ages of driver is 16 to 70, and we're trying to see at what age does a driver's reaction time tend to be greater than 25 milliseconds. So what we would end up doing is graphing this thing. Graph looks something like this. At this point right here, we see it crossing over, and this is at approximately 56.6. So we'll call this 56.6 here. And from 56.6 onwards, right, we see this thing is going up. So from 56.6 all the way to our max, which is 70, is going to be where this thing is above whatever that threshold is. So here, when we set this up, we use 25 milliseconds as our testing time. So jumping into this equation here, we're saying, when is this going to be greater than 25? So we set it up, we subtract our 25 over, we will get this equation here, which is the thing that we have graphed right here. We see it crosses over that 0 at 56.6. So, I mean, in general, we would just call this like 57 to 70. And then that's our answer. So our answer is going to be x is less than or equal to 70, greater than 57. I would argue you could say greater than or equal to 57 here because this is 56.6 that it crosses over, but, you know, tomato, tomato, who cares? That is it for 5.7.